A charge controller is the thing which manages charging your batteries. It takes the power from the panels and then puts it into the batteries intelligently while monitoring all of the conditions. And this chapter is going to be specifically for people using off-grid battery-based systems. A really good way to understand the idea of what a charge controller is to think of it as a battery charger, because really it is a battery charger. It just doesn't plug in the wall. It plugs into your solar panels and charges the batteries up. And these have a lot of intelligence built into them. Here are 3 traditional charge controllers. Each of them can handle a different amount of maximum current or power from your panel system in watts, and they are also at a fixed voltage, in this case for 12-volt systems. A traditional older style charge controller would be used in very small systems, say under 20 amps, and they're inexpensive and they work quite well. The new type are the Mppt charge controllers, maximum power point tracking controllers, and they, through a breakthrough technology, can squeeze up to 30% more power out of your solar photovoltaic array. Now here's an 80 amp Mppt charge controller, one of the really nice top shelf ones that are available to you. And it's heavy duty all the way around. It's extremely intelligent. It allows for data logging of the performance of your system for many weeks, and the connections to it are quite simple. Also, as well, it has a nice LCD display and push buttons that allow you to control all the parameters. That said, it's also very intelligent and simple to use because it automatically detects the voltage of your battery bank, and it can handle a wide range of incoming voltages from the panels as long as the voltage coming in from the panels is higher than the battery bank that it's charging. That's how the Mppt works. Now let's take a look at the connections on a typical Mppt like this. There's our connections there. Really just hooking up the positive and the minus from the photovoltaic panels coming in, and the positive and minus going out to your battery bank, because this is what's charging and controlling the charge of your battery bank. So we're going to show you, of course, exactly the wire routing, but it's very important to know to use the largest wire that will fit into that hole down there. So on this situation, we're going to use 2 gauge and some 4 gauge, and these can easily handle that. Remember, tighten them down, but do not over tighten the connections on these because they are directly mounted on the circuit boards in these cases, so be careful. Also on the left on this one, you'll see that this has provisions for remote controlling with a standard network type of cable. That's an RJ45 designation on that cable connector, and this allows for remote controlling and monitoring of the system as well using networking cable. You can get more information from your manufacturer of your charge controller. Most of them have that these days. One of the Mppt's great features is you may have a pretty long run between your solar panels and battery box and controller. Well, they allow you to run a much higher voltage coming from the array up to the controller, and that cuts down on power losses on that run. So let's review what we've learned so far. Charge controllers come in 2 types, the older traditional type for smaller systems, and the new Mppt type. Charge controllers are rated in E, that's voltage, into the charge controller and out of it, and also the total I, or current capacity of the controller out. Small systems can use a traditional charge controller, let's say 20 amps or smaller, but you could also choose one of the new Mppt small charge controllers and get more power out of even a small system by spending a little bit more money. Mppts monitor and optimize the charging conditions continuously, and Mppts allowed for a smaller wire run from the panels up to the charge controller because they allow a higher voltage coming in from the solar panels. Mppts can give a 20 to 30% efficiency boost to the whole system due to these considerations. And lastly, remember I told you to use the largest wire size that would fit on the output battery connections from the charge controller to the batteries? Do that. But on the input from the array, you're going to look in the manual that came with the photovoltaic panels and find out the appropriate gauge for that, and that's going to be a much smaller size. Chances are you're going to be using one of the new Mppt maximum power point tracking charge controllers, so I'm going to teach you everything about them so you can make your decisions wisely and implement them efficiently. Now remember we said that run from your equipment box with the batteries and the charge controller may be quite long all the way up to that nice sunny position for your panels. You want to keep that under 100 feet if at all possible. Now, an Mppt controller will allow you to run higher voltages than one panel puts out, so you can add them up in series, negative to positive, and thus have a higher voltage and lose less power coming from the panels up to your equipment box. Each Mppt controller can handle up to a certain input voltage. That voltage has to be higher than the battery voltage so that it can push power into the battery bank. Here are the main concepts to understand about these new controllers. In this chart, we're looking at the power loss in the wire coming from the array to the charge controller versus the amount of voltage we run down that wire. If you look at the chart on the left, the amount of power getting to the charge controller from the array is lower if you're using a lower voltage out of the array and becomes higher with a higher voltage coming out of the array. The next concept is that the overall efficiency of the charge controller is slightly reduced as you raise the input voltage from the panels way higher than the battery bank voltage. So as you see from the chart, there's a slight 2 to 4% reduction in the charge controller's ability to make power go into the batteries as that voltage coming in from the panels goes way higher than the battery bank itself. So if there's less difference between the voltage coming in from the panels to the battery bank voltage, the controller has to do a little bit less work in converting that excess voltage that you're supplying back down into charge current for the batteries. Now, this is a small consideration, but you need to remember not to configure your array to exceed the battery bank's voltage by more than about 3 times the battery bank voltage. And the charge controller is going to have a maximum input voltage, so check your manual. And the last concept I want to present is wire power loss coming from the array versus the wire size used. If you look on the left, the percentage of power getting to the charge controller through the wire from the array is lower with smaller wire being used and higher with larger wire being used. Remember that those gauge numbers are inverse, so the smaller number means a bigger wire. So we're aiming for a less than 2% voltage drop coming in from the wires on the solar panels to the charge controller. Your manual with the charge controller will show you charts where at a certain voltage coming down from the panels, at a certain length run, and a certain charging current, exactly the wire gauge you need to run to have less than 2% loss. Larger wire, of course, is better, but we're trying to determine exactly what gauge we can get away with and still hit that less than 2% power loss spec. Let's walk through the decision thought process with what we've learned so far. First, I want every bit of power I paid for in my photovoltaic system. Second, I've already paid a large amount of money for the hardware and it's going to last for a very long time. Third, I know I want to place my panels as close to the battery box as possible for lower loss, but good long sun exposure to full sun is more important than it being close because I can run that higher voltage coming in with a new charge controller and I'll just get larger wire if it's necessary for the low loss. Fourth, if I'm never going to need 12 volts DC for direct use in the house, that means for RV style appliances or amateur radio equipment, I can go with a 24 volt battery system or even a 48. This will result in a higher system efficiency using the same gauge wires, and the Mppt charge controller can easily handle 24 or 48 volt battery bank systems. After deciding on the battery bank voltage, I'll decide on how to configure my panels in an array so as to deliver 2 to 3 times as much voltage as the battery bank, and I'm going to show you how to do this in the chapter on panels. If I go much higher in voltage, say 4 times or more, I'll lose a little bit of power, and I have to know the charge controller's maximum voltage input specification because I don't want to exceed this. Then I'll check the charge controller manual charts to find the wire gauge that I'll need to run from the panels, the panel array, to the charge controller, considering the distance covered and the array output in amps. Now we're going to cover configuring panels in detail in Chapter 10, but let's take a look at 2 typical examples of how you might configure them here. My array is 50 feet from the battery box. I'm running a 24 volt battery system. I'm using 200 watt panels that have a 29 volt output. So I can run either all of my panels in parallel, and that will give me 29 volts output, or I can run 2 panels in series for 58 volts total, because I'm pretty close to the array. Or, number 2, my array is 100 feet from the battery box. I'm running the same 24 volt batteries, The 200 watt panels at 29 volts output, so I should run 2 or 3 panels in series and clone these series sets in parallel until I run out of panels, because you might have 6, 8, 6, 12, a number of those panels. So 2 to 3 in series giving me 58 or 87 volts to overcome that longer run. But always check the maximum voltage input specification on your charge controller to be sure you're not exceeding it. I'd rather use a little bit larger copper wire coming up from the photovoltaic panels to the charge controller and put out a little bit more money now, because I've already spent so much money on the panels and other equipment, to be sure that I'm getting all the power I paid for into the charge controller and batteries. That's my approach. The de facto reality check test to see what your percentage of loss is coming from the panels up to your battery box is, once the system is installed and under full charging conditions, to first take a voltage reading at the panel array, and then go take a reading up at the battery box. Only a few tenths of a volt drop in this system because I used very large wire. That's excellent. You'll need to look at the wire gauge chart in your charge controller manual to determine the size wire you need. You can even parallel smaller wires together if you can get them more cheaply than one large. Here's an insight. Since batteries change their behavior with temperature changes, charge controllers must try to compensate for this by tracking the temperature. How do they do this? With a temperature sensor. A battery temperature sensor mounts onto the battery lug, normally like this on the top left, that copper connection, the black wire going off there, and it allows the charge controller to know the temperature of the batteries to more accurately charge them. When you first power up your charge controller, you're going to have to do a little bit of programming with it, which is explained in your manual. The main selections that you're going to have to tell the charge controller is what battery bank voltage you've set up, and now it may auto-sense it and ask you to confirm that, or you may have to do it manually, and then what type of battery you are using, either a wet cell or a gelled electrolyte battery. The third thing is that some controllers ask you the battery bank's capacity in amp hours. That's the total capacity. Now, it will also have options for you in equalizing charge routine and possibly a fan power output control to blow the gases out of the battery compartment. Because each charge controller is different, we can't cover them all here, but go through the manual slowly. They've made it very easy to do. Plus you can email or call them on the phone, and they're very eager to help you get it set up correctly. An equalizing charge is a deliberate overcharging of the battery bank so as to agitate and mix the electrolyte liquid. The liquid in there can get sort of settled out, and it needs to be bubbled and agitated to mix it up. And it also is done to equalize the voltage of each cell in the batteries. There are many cells in each battery, and they can get to be slightly different in voltage over time. This equalizes that voltage for better efficiency. This should be done periodically, and once a month is a good interval. Your charge controller can handle this completely automatically. An important thing to know about charge controllers is because they have a maximum output current, and that's fixed, but the output voltage to the battery bank is selectable. The higher the battery bank you use in voltage, the more power that the charge controller can handle from the panel array. So you can see with a 60 amp charge controller at a 12 volt battery bank, we're at 800 watts, but as we go up, 24 is 1600 watts, 36, 2400 watts, and 48 volt battery bank, that same charge controller could handle a 3200 watt photovoltaic array. So read the manual to your charge controller several times and thoroughly, and learn the programming sequence. You may have a button sequence, or you may have jumpers to set for the different battery voltages. Remember also that your charge controller is powered by the batteries, so it has to be hooked up to the batteries to come alive so that you can program it. A safety first hit point. Over about 20 volts, your skin has enough conductivity for you to start feeling shocks. 24 volts will shock you if you touch it barehanded, so watch out, especially when wiring panels at higher voltages if you're dealing with bare wires. Whenever you can, turn off the breakers and check with your voltmeter to be sure that there's no power in the wires that you're working on. And don't stand in water when you're working on hot wires. Wear dry shoes and try not to place your other hand on grounded metal surfaces. You're going to avoid making a pathway from the hot conductor through you to the ground. And as a safety rule, don't work alone when you're working on hot wires. Here's our final review for Chapter 8. Mppt charge controllers are the choice for anything but the smallest systems. Number 2, each is rated in a maximum current output, that's fixed, and a maximum input voltage. 3, the maximum current output times the battery bank voltage you select equals the maximum power output in watts. That means that the same charge controller can handle bigger systems if you choose a higher battery bank voltage because it has a maximum current output, and that current output times the battery bank voltage equals the amount of watts that it can handle. Every time you double that battery bank voltage, the capacity of the charge controller goes up. So if you're going with a higher battery bank voltage, it's a good idea if you can. Number 5, the photovoltaic panel array power output, its voltage, its distance from the battery bank and equipment box, and the battery bank voltage is going to determine the wire size. And 6, charts in the charge controller manual show you the correct wire size for less than 2% loss on that run. That's what we're shooting for. Number 7, panels can be configured in many ways to select a voltage output. So you've got a lot of choices there in the way you're going to put them together. Number 8, try to be minimum 50% or so higher in E. That's the voltage coming in from the array than the battery bank voltage. But remember, not more than 2 or 3 times as much or you'll lose a little bit. Number 9, if in doubt, go to the next larger size wire for the feed-in. It costs a little bit more, but you really want to have the least amount of loss in that run. And number 10, the charge controller manuals are excellently written and the companies are very helpful. So read through the manual several times and call up or email the company. They will talk to you forever on the phone, being sure they get all of your questions answered.